started. Thank you all for coming. My name is Ian Cook. I'm one of the co-organizers of the RTA group, along with Eric Yount, Melinda Thielbar, Dan Kelly, who's not here today, Rick Pack, Aaron Terry. Did I miss anybody? I don't think so. Anyway, we meet on the third Tuesday of most months. This is actually the last formal meetup we'll have this year. In November, we typically have just a party to celebrate the group, thank the members. So watch out for the meetup announcement about that on November 19th. We skip December, and then we'll start again with meetups in January. If anyone has talks that they'd like to present, please come talk to one of the organizers or send us a message, and we'd love to consider your talk. And if anyone has suggestions for venues also, we're always looking for good spaces to meet up in. Chris Calloway of Renzi is generous enough to give us this wonderful room, but we're always looking for similar spaces that can hold about this many people in various places in the Triangle. Also, every March, this group hosts a unconference called Analytics Forward in Durham. Has anyone, raise your hand if you've been to Analytics Forward. It's a really cool conference with a lot of folks. And we're going to be back for the 6th year in it's March 2020. And we will have, I think we can announce the keynote speaker for this year, who will be Dr. Robert Earhart, who's a climate scientist at Wake Forest. And he's going to speak, I guess the title of his talk, his keynote talk, is going to be Being Right Isn't Always Enough. Other requirements for adding value through climate data science. So it should be really interesting and topical talk. After the talk today, we will have an after party, as we typically do. It'll be at Monterey, which is in Rams Plaza, sort of just behind where we are now. But Chris has reminded me that the service road that's between 15501 and where we are now is closed. So the way to get to Monterey is to turn right when you exit, and then right into the rear entrance of Rams Plaza. So there's a map up here. Just put Monterey Mexican Restaurant, look for the one that's in Rams Plaza, and that's where we'll convene afterwards. So without further ado, I will introduce our speaker tonight, who's Kieran Healy. So Kieran is a professor of sociology at Duke University, and he studies the basis of self-interest and altruism as it applies to all sorts of interesting things like blood donation, organ donation, but also donation of time for things like open source software projects. Kieran's also interested in software and methods, particularly data visualization, and he's the author of this really excellent book, Data Visualization, A Practical Introduction, which I think does an excellent job of sort of stitching together both the practice, you see a lot of code with R and ggplot2 in this book, but also the principles, the concepts underlying the point of data visualization, which is communicating information. So highly recommend this book. It's available on Amazon and other booksellers. And I think with that, I will introduce Kieran, and you can take it away.
Thank you, everybody, and thanks for the invitation to speak. Thanks, Ian, and all the people at RTA, and thank you all for coming. I was asked to give a sort of general talk about data visualization, which covers a very broad range of potential topics. And I guess I'll focus on, or talk a bit about what makes some visualizations better than others, is the sort of basic question I get a lot when I'm thinking about this material. I know that in a room like this, a lot of you probably are much better coders than I am, or know there's a lot of range of knowledge and practice and focus of application when it comes to things like data visualization. So hopefully I'll be working at a level where this is something of interest to say to everybody. As Ian mentioned, I do most of my work in database in R, which I realized today that I've been using since it was a different letter. Since it was S, which is sort of a disturbing thought. But R has changed a lot over the last 25 years, and recent developments, particularly this whole sort of suite of tidyverse tools, which the book is focused on teaching people, have really kind of made R a tool that much more people can use in a much less frustrating and much more straightforward and powerful way. But I won't be talking too much about the nuts and bolts of that this evening, at least not. If people have questions, I'd be happy to But we'll step back a little bit and sort of ask the more general questions about why we want to look at data in the first place, and what it is that makes some sorts of visualizations better than others. Now, there are a couple of kind of canonical places to start when it comes to questions like this. One of them is this. This is Anthems Quartet, which is a little deliberately constructed an artificial data set of 4 sets of pairs of x and y points that were sort of artfully constructed by Anscombe quite a while ago now. And the idea is that if you just look at the numerical summaries of each of these pairs, the x and y pairs in the panels here, then you find that they all have the same numerical properties, at least at first glance, right? That when it comes to summary statistics, right? The mean of them is the same. The n is the same if you fit a regression line to them. You'll get the same line. But of course, if you just look at a scatter plot, in this case, then you see that if these were real data, you'd say, well, clearly a different process is responsible for producing these data in each of these cases, right? And so it wouldn't be sufficient simply to look at numerical summaries of our data in order to get a full picture of what it is that we're dealing with. So you should look at your data, and you might discover things about it that are unexpected. This point about Anscombe's quartet was kind of recently generalized into Datasaurus here, which some of you may have seen, which was put together by a couple of researchers. The idea being that you can just sort of start to, again, constrain your points. A couple of computer scientists go with a nice algorithm for where you could set the quantities that you wanted to preserve and then mess around with the points. Although, in fairness to Anscombe, the reason that Anscombe's quartet in particular is interesting is that you would get sort of apparently significant relationships between the correlation here, or degree of association, right, between the points is basically 0, whereas with Anscombe's quartet in most cases it's a respectable 0.7 or something, and which is harder to artificially achieve. And this, in the social sciences, which is my sort of background, this you might think that we're all used to looking at our data now, and that we're aware of the benefits of it. But both in the past, which this example is from, and right down to today, where I saw a whole bunch of papers in biochemistry are about to get retracted because of a mistake in a Python script that was accidentally mismatching pairs of data points, dyads. Looking at your data can really tell you a lot about what's happening inside it, rather than relying on summaries. This is a paper by a political scientist named Jackman who wanted to make an argument about the association between voter turnout and income inequality in a bunch of different countries in the 1970s, and made the argument purely numerically. Got published in a prestigious social science journal, and then this is essentially the entirety of a comment that was published about a year later, and by a guy called Hewitt, who he fleshed it out with a few paragraphs, but this was essentially the argument that South Africa was driving the results, right? The apparent association between the two variables was really been driven entirely by the presence of a significant outlier in the data set. So it's worth looking at our data, but when I talk about this material and when I teach to other people and to students and to practitioners, I also emphasize that data viz has become extremely popular in the last 5 or 6 years in particular, and there's always a danger that you can sort of oversell what you can get from data visualization. Visualization is just a tool, and the tools that we have, they can't make you right and they can't make you honest, right? They can help you in that direction, but there's a reason that we have numerical summaries of variables, and there's a reason we have statistical models and other methods for looking at data in different ways. Sometimes you want to see past a cloud of points or an apparent association visually and establish whether there really is, by some statistical standard, for example, an association or something significant or something worth pursuing in more detail. So it's not the case that visualizations are some sort of panacea that just by looking at what's in our data we'll see what's really there. As we'll see in a minute, quite the contrary often, because of the way that we have to see, or because of the way that we do look. And so that's one side of things for sort of professional practitioners, which is the point that data visualization is just another very useful, increasingly easy to use, and versatile tool that we deploy when we want to examine our data, and that's often worth it, but not a piece of magic or anything. And then on the other side, there's the point that looking at visualizations like this is a skill that we learn, right? It's a kind of language that we learn how to speak, and that there's a rhetoric and also a syntax and a semantics of visualization that when we're looking at data ourselves, it's often easy to forget if we're very used to looking at certain kinds of representations, like scatter plots, for example. We understand, I'm sure everybody in this room has seen data like this before, and they know that there's an x-axis and a y-axis, the points, individual observations are plotted, and then we can assess some level of relationship between the two by looking at the shape of the distribution or the shape of the joint association in the points. But that's not something, obviously, that you just know. You have to learn it. And it's easy to overestimate when you're presenting data to larger audiences or the wider public, just how familiar people are with what we might think of as kind of ordinary common or garden visualizations. And there's surprisingly little research done on the extent to which that sort of data visual literacy is widespread or well established in the population. This is one of the very few efforts to sort of deploy on a representative national survey by the Pew Research Foundation. They showed a representative sample of Americans this graph, and asked, which of the following statements best describes the data in the graph below. And you can see you've got average sugar consumption on the x-axis, the number of decayed teeth per person on average in different countries on the y-axis, and the plot between them. The correct answer is C. The more sugar people eat, the more likely they are to get cavities, is the association. And amongst those surveyed, well, about 62% of adult Americans got the right answer. And the other third chose something else or said they didn't know. And so when it comes to producing visualizations for different audiences, you have to kind of understand, or you have to be aware that not everybody is going to immediately grasp the meaning or significance of what it is that you want to convey. And that charts and visualizations of all kinds are something that you have to learn how to read. Alberto Cairo has a book out called How Charts Lie just this week that sort of starts from that premise, that tries to increase people's visual literacy in ways that charts of the ways that charts can often go wrong. So some charts are better than others. We have that intuition, and so we can ask what it is that makes some kinds of representations, some kinds of graphs or visualizations more effective than their counterparts. And so this is where we start to kind of eat into any kind of bland, complacent presumption that just by visualizing our data we'll get a better sense of what's inside it, right? Because there's all kinds of ways to look at things that will not give us the right answer. One place we could start is a 3D bar chart in Excel. This is a default. This is not Excel's default bar chart, but if you ask it to present or to produce a three-dimensional bar chart for you, it will do this. Maybe you've made one yourself, or maybe you've seen a presentation that incorporates data like this. I ask people in these kinds of talks, to sort of guess or to just tell me what they think the values of A, B, C, and D are in this graph. And of course, when speakers ask you these questions, you know that it's not the obvious answer, and that's true in this case too, because of the way that Excel constructs its this sort of isometric view, this outside looking down from the top or from slightly above the graph view. You get a very strange impression. So it seems like, right, for B here, well, are we supposed to look at this, or are we supposed to look at this at the top? It's hard to assess. If the numbers if some important thing actually turned on knowing the right answer just from looking at the graph, then not very many people would correctly intuit the right answer. It doesn't seem like any of the lines intersect successfully, despite the fact that you can try this yourself if you have your laptop. Despite the fact that they draw two sets of grid lines for you, but the one you're supposed to be looking at sort of like projects out invisibly across the front of the graph, right? Yeah, it's you can try it yourself. You probably have Microsoft Office installed, and this is its standard behavior. Pie charts are another common target of abuse from people like me, and here it's less that there's a different set of issues is raised or are raised where it's not so much that you can't quite assess where the line should be, but once a pie starts to have more than a couple of slices, and in particular if they're if some of the slices are roughly the same size, then it becomes harder than it should be to make an assessment about which slices are correct. And again, if the difference matters, for some sorts of data, for some kinds of question, the difference between 15 and 25 or between 20 and 25 might not be that important, but for others it might matter a lot. And so if you're showing these kinds of results in a format where the viewer has to work very hard to understand or to estimate what the quantities are, well then that's a problem. And so there's a whole sort of family of bad visualizations like this, or at least problematic ones that I could show you, but it's better to sort of step back and ask, what is it, or how should we think about the different ways that visualizations might go wrong? And I'll approach this under sort of three headings that are related, but they're independent enough that we can approach them sort of one at a time. And so the first is visualizations that are in bad taste, that really just look terrible, that are an offense against your finely developed aesthetic sensibilities. The second is the sort that rely on bad data, or the wrong data, or that they're presenting the wrong thing to you, even if they're doing it in a tasteful manner. And the third category of badness that I'll talk about is visualizations that trick us in some ways because of the way we perceive things, because of the way the eye works, because of the way our human visual system will process information and how it can be misled. And this is all kind of mostly prior to, often prior to the intent of the person presenting, or it's independent at least of the, in principle, of the intent of the person presenting the visualizations. These are things that can affect people regardless of whether they set out to deceive you or not. So, starting with the bad taste, the tastemaker in this area over the last 35 years has been Edward Tufte, and former political scientist turned full-time data viz guru who in '81 wrote The Visual Display of Quantitative Information, the modern classic that's still very much worth your while. And his approach was very much kind of a taste-based critique of bad visual practice as it existed in the 1970s. And he sort of wanted to derive various rules of thumb that explain to people how it is that they should proceed, and sort of simplifying the chart to the degree that, to the greatest degree that you could, was the way that he proceeded. He was particularly interested in and railed against what he called chart junk, right, which was excessive visual information in charts that didn't contribute to the data being displayed. This is one I made myself in Keynote. Got a nice quality wood grain here. I've got a shadow coming from, even the numbers have shadows, which is nice. They're casting that papyrus font, right, your off-brand herbal tea label font, and multiple colors. In the end, there are 5 numbers displayed on this chart, right? And that seems to be too many. And Tufte took aim at a number of similar visualizations. This one is by Nigel Holmes, who is an information designer who's still working and producing very interesting stuff right now. He's mostly sort of really interesting instruction manuals and guides and things for how to assemble stuff and how things work, that sort of material. But Tufte really hated his approach when he looked at, again, summarizing small amounts of numbers in this kind of excessively flashy and in Tufte's view, needlessly junky way. And it's true that we can take a visualization like Monster's cost here and boil it down to its essence, which is just a small number, and you get something that's substantially, more easy to interpret, certainly less visually compelling. In recent years, we've had research that's kind of complicated our assessment of flashy visualization work, because people remember things like this much better than they remember things like this. And that's not something that's irrelevant when we're presenting information. Yeah?
There's also the concept outlined by thinking fast, thinking slow, that the things that are more difficult to actually read and interpret while you're reading them are actually more memorable.
Yeah, and so in some circumstances, right, people like Kahneman it says you can activate your system 2 thinking, right? That instead of just processing it immediately, then if you have to work a little bit, then you're more likely to remember it. It's not clear to me that the evidence that we have about how visualizations work, how that fits with the kind of thing that that he has in mind, because again the visual vocabulary of charts is one that the reader needs a certain amount of guidance, not sort of added complexity. Charts can have a content-based complexity, for example, that's independent of their design-based complexity, put it like that, so that you can show it. A chart can show a lot of information and require study in a way that would require the kind of careful thinking that you have in mind, and that could still be an excellent piece of work. But in its design framework, it would need to be straightforward, I think, in a way that was easy to read, so you wouldn't want to waste time kind of trying to figure out what it was the chart was trying to show at a very basic level. And that's why, for example, we know from some research in this area that if we take, for example, variably charts that vary in the amount of additional or strictly superfluous design or signpost information that they present to the reader, or the viewer, then people perform more or less well on the when it comes to interpreting them. So, for example, and this is not inconsistent with what you're saying, I think. So here we have sort of the same data in 3 different box plots, right, or pairs of box plots, where we're showing in the traditional box plot as developed by John Tukey in the 1960s and 70s. You've got the box showing the median value for your distribution, the 25th percentile, the 75th percentile, and then extending out usually twice the interquartile range, I think, is where the whiskers go. And Tukey, of course, was working in an era when he wrote this book in the 70s called EDA, Experimental Data Analysis, and it's really interesting to look at it now because so much of it is about figuring out ways to represent data when you have to calculate it by hand, and when you have to sort of get numerical estimates sort of with a pencil and paper. And so things like this 5-number summary of distributions they have their origins in hand-based calculations of trying to get a sense of numbers quickly. Stem and leaf plots, which he also invented, which you might remember from high school or college, are also about sort of just quickly scanning tables of data as quickly as you can. In these cases, you've got 3 sets of box plots. This is sort of a more contemporary version of the box plot that retains a lot of information about the axes, that thins out the median lines, makes these the whisker lines solid, removes the little dynamite handles at the bottom of the plots. And these are a version that Tufte developed, trying to maximize what he called the data to ink ratio in the plots that uses kind of negative space to imply where the 25th and 75th percentiles are, and a dot rather than a line for the median, and also removing as much of the axes as you can. And this doesn't perform as well. People have a harder time interpreting what this means, even if they already know what a box plot is. And it's the scaffolding provided by the familiar axes and additional information helps people to understand what's happening. And so this suggests that just having sort of really elegant data to ink ratio maximized, purely designed minimalist plots isn't going to be enough for us. And we can see this in a couple of examples. One, I'll just show. This is from an article in the New York Times from a couple of years ago. The political scientists Yasha Monk and Roberta Sevenfoa wrote this article about the decline of democracy in several advanced industrial democracies in a bunch of different countries. They presented a version of this figure, which the Times then cleaned up and redesigned. This figure is very nicely designed. It has no junk in it. The Times is their graphic design department is extremely good. And so you can see that the points are showing sort of the decade of birth of individuals, and then the percentage of people who say it's essential to live in a democracy. You can see it seems to be the case that as the people who are asked are older, they're all asked at the same time. So this is not sort of a longitudinal survey; it's a cross section where you ask people of different ages in the population at once this question. and it seems to be, things seem to be declining in some way. When political scientists who were aware of the data source for this, some of them got a little annoyed because it seems like, from the way that the information is being presented to you, that people were asked a question: do you think it's essential to live in a democracy or not? Yes or no? And then this is the number of people who said no to that question. When in fact, the World Values Survey that asks this question says, on a scale of 1 to 10, how important is living in a democracy to you? Which is quite a different question. And if you sort of put the scale back in, as Eric Wooten did, then we see that the decline that Monk and his collaborator identified is certainly there, but in the context of the actual question, then it seems like, well, maybe it's not quite as severe in some countries, or maybe at all, as it might have seemed. And perhaps if the original journal article had a graphic that looked like this, as opposed to this, then it might not have had the legs that it turned out to have, right? And so what's wrong with this chart is not anything to do with its design or the way that it's conveying information in terms of the strictly graphical elements. It's more, what is the link between the visualization and the underlying quantity or data that's being represented? And if that isn't held, or if we're thinking that that's being stretched a little bit, well then no amount of good design will save you. And indeed, there's a rhetoric, again, there's a rhetoric of plausibility to well-designed charts. If you're used to looking at bad charts and you see well-designed ones, well then that increases your confidence, and you're more likely to have your system one say, yeah, that's probably right. I'll store it with the value of true in my head, and move on to the next thing. So this question about kind of the relationship between taste on the one hand, the underlying data on the other, and then the third component that I want to talk about in ways that visualizations can be challenging is the matter of perception, right, which is more like the mechanics of how we see things when we look at them on average. And so this is more like at the level of our visual system and how we can expect it to work, and how things that we know about our visual system can play into how we ought to design and think about the charts that we see. So when people like Tufte and others were writing in the 70s and 80s originally, research on the relationship between cognition, right, how we actually grasp mentally and understand visual elements, and data visualization was in its infancy, almost non-existent. It was really just getting off the ground in the 1980s, and we've come a long way since then. So there's a lot of useful information that we've learned. And so I'm not a vision scientist, and so I'm not going to pretend to be. I'll pick out sort of a few things that we know from that literature that are relevant to the way that we look at data. And some of these effects that I'm going to show you might not work in this room for everybody because this is quite big, and so they're a function of where you're sitting and what your perception is like. And so we've known since the 19th century that the human visual system is an active feature of our brain. Right? That our eyes don't simply kind of absorb what's out in the world objectively and transmit them on a movie screen inside our heads. Right? That's not how vision works. And we've known, for instance, that this is a Hermann grid, and the Hermann grid effect is one where if you're sitting at the right distance, you start to see little dots, little ghost dots at the intersections of the white little roads here, but only when you're not looking directly at them, right? They're sort of after images. Or we can see, for example, in these cases, your brain is trying to kind of put together, it wants to see diverging lines, but in fact, the pattern is just repeated across the screen, right? And so it seems like you want to see the thing in one way, but the way it's constructed is kind of deliberately confusing your head. This is a Fraser column illusion. There's a whole family of these. This is another Fraser illusion where you want to see sort of diverging or converging roads, but they can't. But it's just because the way that the black and white patterns are alternating is working deliberately to confuse the way that you want to see where objects are in the world. You can do this dynamically too. This is the Muller-Lyer illusion is one that you might be familiar with, where there's line segments, and depending on whether their endpoints are angled in or angled out, then people will judge the line to be of longer length if they're angled out. If we make this dynamic, you really can sort of see, even though the line lengths are not changing, the whole thing appears to be pulsing in a way that is confusing to people. Closer to the level of visualizations that we might make, this is an illustration of Mach bands. So our visual system is good at detecting contrast when there are contrast between adjoining or adjacent elements, right? Where our visual system is not very good at being a light meter, right? So grayscales vary in how much luminance or how much light they're reflecting back at us. And we're good at detecting contrasts between them, but we're not very good at establishing how much absolute light there is or how much absolute luminance there is in a particular image, right? That's why photographers have a little light meter that they carry. Yeah?
Do Tufte's argument for simplicity include these perceptive problems that are introduced by additional information?
I think not initially. He was more focused. He had very strong and very good intuitions about what made for effective graphics, but it wasn't grounded in cognitive science or in any experimental literature. It was more like he could see as a practicing social scientist to begin with, and then as somebody with a very well-developed design sense, kind of what was working and what was not working. And so in this case, for example, if we just by making the gray scales adjacent to one another, we become much better at perceiving the contrast between them. I think, right? That if you can tell that the gray scales are moving from darker to light on the left-hand side, but just by having them share a border, well, then the apparent contrast becomes stronger in your assessment, and that can matter. For example, if you're constructing a map or some other distribution of data where you have some discrete gradient like this in a series of steps reflecting the value of some variable, and so you might want to take advantage of a feature like this, allowing you to emphasize the contrast between categories, or you might want to make sure that you're not accidentally seeing more of a contrast between two categories or two regions of a graph simply because they share a boundary, right, rather than of any absolute difference in the value of the data that's being represented. And
you're saying the one with the borders attached, I'm supposed to be able to see the difference more than the other one.
Yeah, so experimentally we know that and again, in environments where light like this is harder to control, the effect is one where if you present people with swatches like this and ask them to assess the relative difference between the grayscales, they're better at doing it when there's shared border. They can distinguish, for example, finer gradients and finer differences if they share a border.
If they share a border.
Yeah.
Okay. So you're saying that my perception right now, because the reason that I ask is when I look at this,
it's the other way around.
Right.
Yeah. And so that it's a function of how far away you are from the from the image.
Okay.
This is a feature too of presenting material like this, or presenting visualizations in general. Not in this talk, but elsewhere, I talk about thinking about giving talks and thinking about presenting data. The color schemes that you rely on, grayscale, contrast that you want to bring out in talks. It's a very different business when you're looking at your beautiful retina screen here that's extremely bright, right? That's presenting like a lot of backlit luminance at your eyes, and then you can make sharper distinctions when your screen is bright. Like if you have a nice new phone, you'll see that the quality is better. Whereas if you're in a room like this that's ambiently lit, and the projector, though powered by a really bright bulb, is not able to compete with the ambient light of the room in the same way that your phone can when it's like 3 or 4 inches in front of your face, and you can't make the same sorts of fine-grained distinctions. And so things that contrasts that pop out on your screen or on your phone won't on a screen like this unless the engine powering it is much brighter. And so these luminance tricks, because the eye is not a light meter, this is a famous illustration by Edward Adelson that hopefully you'll be able to see in this case. And so the idea here is that that this checker squares marked A and B are the same shade of gray in both images. And this is supposed to help you sort of see that, although people generally tend not to believe that, that it's the same, that's the same image. So we can zoom in on this one, where you can agree that it's not, they don't look like the same shade of gray at all. But if we zoom in on the image, and I promise I'm not, conning you, then in fact their luminance is identical. And what's happening here is that, as Adelson himself says, your eye is not a light meter. It's designed, it evolved in order to tell what real objects are in the world. And one of the questions it has to answer is this a dark object in bright light, or is it a light object in shadow? And which is which, right? And so when you have alternating checker patterns and an apparent solid casting a shadow in an area, well then you can fool the grayscale detection that your eye uses into thinking, well, this pattern seems to be alternating, so this must be a light square, and that's consistent with the other visual information that I'm getting from the image, and that is for the same reasons that's the dark square up there, even though in fact, in absolute terms, they're the same shade of gray, right? And so that's something that we, so we're not very good at making those kinds of distinctions in practice, and that's something that matters when it comes to assessing images. For example, we're much better on the whole at detecting edges when it comes to grayscale than when it comes to color. So in fuzzy images like this, color can be very effective, or at least directly competitive with the grayscale image in terms of our ability to see kind of this sort of cloudy fuzzy image. This is from Colin Ware, these images. But if we introduce edges in the image, then even if we're not kind of red-green colorblind, our ability to detect and distinguish edges is much stronger in black and white, in grayscale, than it is in many parts of the color spectrum. And so that's something that we have to think about too. Color is its own very complicated world. Color theory is fascinating and difficult. There are a bunch of color. Again, the active nature of our color perception is something that is easy to grasp. If you keep staring at this, let's see, this is the Troxler effect, this is called. If you keep staring at the, and again, I'm not sure if it's going to work in a room like this. Keep staring at the black dot for a while, what tends to happen is that the colors will just disappear from your image, and you won't be able to see them anymore. And they'll go away. You get the same effect if we set this running. That might be more effective on with the rotating one. Similarly, the spots will just tend to disappear if you focus on the cross for a little bit, and your eye just is unable to. So whatever it is that your eye is doing, as a vision scientist, it's not just simply a matter of objectively rendering what's there in front of you. This comes up specifically in the world of data visualization in a variety of ways. Our color perception is not uniform across different parts of the spectrum, and the inferences we make about what's important and what's not important are dependent on the colors that we're being shown. And so this is a rainbow gradient, which is used still in many parts of the natural sciences out in the world, the National Weather Service, right, for indicating different kinds of, it has very poor perceptual qualities. And the main basis for its poor perceptual qualities is that the way that we see when we look at the components of an image, it's partly the hue, right, whether it's blue or red or green. It's partly the intensity of that color, kind of like its saturation or chroma. And then there's the luminance, the actual objective brightness, which we're very poor at discerning of in parts of the spectrum. And for some parts of the color spectrum, we're better at distinguishing different kinds of different levels of luminance than others. And the trouble with these kinds of spectra is that their perceptual qualities are not uniform. So a move from here to here in perceptual terms is not the same to us as a move from here to here, even if it's the same in absolute magnitude. And when we're presenting data, we have some set of numbers that we want to represent by, in this case, some set of colors. And what we want is the relationships between the numbers in our data to be preserved, right, in the mapping to the colors that we choose. And what that means generally is that we want a step of a certain size in our data from one value to another to be somehow reflected or faithfully preserved in the in the steps that the color gradient takes, right, from one step to another. And that's harder to achieve than you might think. Let me show you an example. We work very hard in a lot of visualization to try and design color palettes. These are from Or's color brewer package. That where the step from left to right is a sort of linear decrease in the perceived luminance of the color, right? And so that we're steadily moving from dark to light in perceptually equal-sized steps, even if we're not doing so in strictly numerically equally sized steps. This came up in the news recently, unexpectedly, with this image, for example. Here's Hurricane Dorian. And so we saw different ways that this data visualization was manipulated by people in authority. But this uses your standard sort of rainbow scale. And if you think about sort of what this is doing to you perceptually, if you're just looking at it as a naive viewer, it's not clear. Well, is the darker green and the lighter green, is that less or more? We know that it's probably less, right? Because that's, you know, as the thing fans out. But that's not how we're really perceiving it. If we replace this, and the same goes for the pink and the reds here. This is much more salient than it should be, this red, as is this green, right? Much more salient than it should be, given its actual position on the spectrum or gradient that we're trying to represent. If we replace this with a very close but perceptually uniform, luminance uniform color scheme, we get a much better sense of where the stepwise decline is. And there are a variety of palettes that we can use that sort of have this property of steadily decreasing in a linear fashion the apparent luminance or brightness of the image. So here, for example, is the original. This is the original color image, the rainbow palette one, converted to grayscale. And here you can see, right, like if this were a well-functioning gradient, converting it to grayscale these would be the darkest, and we would move out then to the lightest areas, right? That's how it ought to work. And this is what I mean. But if we take our standard rainbow color, this is what I mean by when I say that the luminance, relative luminance of the colors is kind of wandering up and down as we move across the spectrum, when it should just be decreasing in a linear way to reflect what we want the gradient to show. And so, for example, as I say, this is the color version. Here's a black and white version of the original rainbow. If we have a black and white version of the better, more color balanced, luminance balanced palette that I showed you, then you get the property that you want, right? That it's linear as we go down. And there's different ways to, as I say, there's a bunch of different palettes that have this property, and it really matters because if you're looking at data, then often as a practicing scientist or researcher, you want to find things, and you'll find them. You know, if you want them hard enough, and that's not good. And some features of the tools that you use, like for example, working with a rainbow palette, will encourage you to see things that are just not there in your data. And so up here we have looking at both continuous and binned or pixelated sort of versions of data with the rainbow palette, and then down here we have one of the Viridis palettes, which is this nice, properly balanced palette. And you can see that the apparent intensity of the differences, it's still there, but it's not nearly as eye-popping as it might seem up here. And so that's both something that's at the level of your perception. The reason this looks this way is because of these bad features of the perceptual features of the color scheme, but that also feeds in to either encouraging you or encouraging your audience to see things that are perhaps not actually there in the data. Let's see, so I've got 40 minutes, so we'll take about 5 more minutes. I'll talk about one more feature of our visual system that's relevant, not so much in terms of misinterpreting data in the way that I've just been talking about, but maybe helping you as a presenter show things to an audience when it comes to looking at data that you want to show. And this is the phenomenon of pre-attentive processing, or pop-out. And so the theory behind this with respect to data analysis is that we have different channels, right, or different graphical elements that we use to present different variables or measures in our data. So we can represent things by points in space, we can represent things by shape, we can represent things by color or length, right? And in each case, we're taking data that we have and trying to sort of faithfully represent some feature of it using the visual elements that we can see. Color is very effective, in part because the way that our visual systems work, we're very quick at seeing certain things, and we have to work a little harder to see other things. And so color pops out. In this case, for example, if we have 20 orange circles here and one blue one, you saw the blue one immediately, and you didn't even have to think about it. It's just like, there it is. And if I increase the number of points, you still see the blue one immediately. The blue circle is very, very easy to see. It pops right out at you. And that's a sort of feature of your visual system that's independent of your system 2 thinking, right? It's not, you don't have to consciously engage any part of your brain in order to see these things. We can encode the same sorts of data with shape, right? And there's a blue circle here too. It's a little bit harder with shape, right? You still see it pretty quickly. There's a blue circle in each of these pictures. But shape is not as effective as color as a channel for kind of encoding information for pop-out. If I increase the number of data points, it's still possible to find the blue circle, but you have to work just a little bit harder. You can feel yourself, looking for it and scanning for it. And so there it is, right? In case you haven't seen it. And if we combine shape and color, well, then things become much harder, right? And so there's still a blue circle, but now the joint search of looking for the blue circle in the field of yellow triangles and yellow circles and so on is a much harder task. There it is. And so these are features of our visual system that we can sort of leverage in an honest way to our advantage when we're trying to draw attention to people's attention to features of our data that we're interested in. In each of these cases, I got this example from Tamara Munzer. There's a sort of hard task and an easy task, and you've already completed the easy task, right? Just by looking. But there's a harder task in each case, right? Where perceptually it's harder to see the inverted T than the bold one. It's harder to see the reversed angle than the highlighted one. It's harder to see a particular slope, right? As opposed to the thing that looks like a T already, because you're used to looking at the letter T. And particularly on big screens like this, it's hard to see this particular shade of green amongst all of the others, right? So you can sort of pick them out one at a time. That's probably the hardest task on a screen. And so we have powerful tools when we're presenting data, and they allow us to do things like combine multiple variables into multiple different channels in order to show a whole bunch of information at once to people, and that can become overwhelming to readers very, very quickly, right? If you encode on position, on shape, on size, and on color, then unless your data has a tremendous amount of structure in it, and perhaps even then, it's something to think twice, but you can overwhelm people's ability to decode what it is that you're trying to show them. So that's the basis of a lot of what we know about the visual tasks that people have to perceive or to complete when they're representing data on a page. And so for some sorts of tasks, it doesn't matter how tastefully constructed your graph is. If the perceptual task you're asking the viewer to accomplish is a tricky one, right? And so for these kinds of stacked bar charts, for example, because the red category here at the bottom, series 1, share a baseline, it's easy to see what their relative heights are immediately. But because these guys, the green ones, for example, don't share a baseline, it's much more difficult to judge if this one is bigger than this one, for example, and by how much, right? You'll guess incorrectly more often than not. And that's true even if we strip out all kinds of features and just get down to the bare bones of like which line is the longest, or order these lines. If these all shared a baseline, you'd be able to tell instantly, right? But because they don't, then that's a much harder task, right? Comparing lengths in space like this. Similarly, features of our data that confuse us perceptually. In this case, if you ask people what's happening to these two series, they'll tend to say that they're converging over time. If we extended things a little further out, then perhaps they'd cross even or meet. But in fact, the apparent convergence is entirely a function of the aspect ratio of the graph. And so if we just pull it out a little bit, then you see that the distance between them is, and this is the same series, is constant, right, throughout. One of the reasons this happens is that when we're comparing two lines in rates of change, we compare kind of the wrong angle, right? We should be looking sort of we look at this distance, and we should be looking at this one, right? As we go, and so we tend to make incorrect inferences about what rates of change are. And so we know now from quite a bit of research in this area that certain sorts of mappings for data are more effective than others when it comes to presenting things. Here's a rough hierarchy again from Tamara Munzer, is a computer scientist at UBC. When it comes to representing continuous data, certain sorts of usually simple representations are better than others. Position on a common scale and length, if they share a baseline, those are easier for us to judge accurately than things like encoding one-dimensional numbers as two-dimensional areas, or especially, here's our 3D bar chart, right? Because we're looking at sort of apparently solid objects, we're very, very poor at judging the relative difference in the actual value being represented, right? Because volume goes up with the cube of length, right? So it seems like things are much bigger than they are. The same goes for categorical variables, where we have things like position in space is easy for us to tell apart. This is over here versus this is over here. The range of and shape performs much more poorly than color. Although the range of kind of poor performance here is not as bad, or as wide rather, as the range of poor performance here. So shape isn't as bad as volumetric representations are bad. And so that's where I leave it for the end point. Let me just quickly return to this question of kind of honesty and good judgment. Like, these features of data visualization come into play when it comes to designing rubbish like this. If we can simplify it, and we can say, well, here's one way, for example, to represent our life expectancy data as a length, where we have a bar chart and we have the life expectancy goes down to 0 here and up to the maximum value or just over it here. Or here's another way to look at it, right? With Cleveland dot plots. Both of these plots are well designed and effective in conveying information. One of them goes to 0 and it's a bar chart, and the other doesn't. Now, which we think is, some people think that this is that it's always dishonest to display information like this as without showing a bar. On the other hand, you can very reasonably make the argument that there aren't any countries or continents in the world where life expectancy is 0 or 5 or 10, right? And so this is sort of irrelevant to the comparison that we want to make, which is at the actual distribution of the data at the upper end. And the decision about what to do is the kind of rules that we have are not like they're not like the perceptual stuff, they're not like laws of nature, but they are, it's usually a question of asking yourself and understanding what your audience is going to see, like what is the relationship that's theoretically interesting or substantively interesting in your data, and what is it that you want the tools that you have at your disposal to draw your audience's attention, attention to. And for some sorts of data, this kind of representation, for most sorts of data actually, I think, is perfectly fine. And insisting on things like, for example, a 0 baseline is not that helpful. There are multiple examples. The best, I think, is if you look at the global temperature series over the last few hundred years. Well, if you just look at it in degrees Kelvin, for example, or go down to a 0 baseline, it seems like nothing's happening. And so it's a substantive question how to make these kind of choices. Yeah?
Yeah, I kind of want to wait to the end for this question about
I'm just about done, so.
Yeah, no.
Go ahead.
My question kind of revolves around, so I feel like a lot of these visualizations and worst practices and things like that are relying on our, like you said, kind of distances and proximity and things like that. Whereas, we talk about a lot in visualization, the art of just direct labeling. So almost every single one of these charts, especially in the past two, could be immediately solved if we just put a direct label on there and get rid of the axis. What is kind of the best practice for over direct labeling versus allowing, because I think you mentioned this in one way or another, decreasing cognitive lift, how hard we make people work for the data. So we're obviously not giving them a table of data, but providing direct labeling.
Yeah, that's a good question. I mean, and it's hard to get it. I'm not going to give like a hard and fast answer, but it is. So if you're interested in designing visualizations, then generally you're going to resist a lot of direct labeling or direct labeling for all of your data, because if things are radically improved by simply labeling the values at every point on your data set, then you're probably designing the visualization incorrectly, right? And so I think you're right about that. And then the question becomes, well, what do I need to do, especially if I'm presenting a great deal of data to somebody, and I can't label everything. And so for example, in a plot like this one, yes, you could just label. There's only 5 data points. So this is a sort of minimal case. And you could just label directly and not worry about the questions that I was talking about. In a plot, in the same case, for example, like this one, this is law school enrollments in first-year law school enrollments in American law schools from 1974 to 2012. And so, so this is they went off the edge of a cliff in the wake of the financial crisis when a whole bunch of companies rescinded job offers and everybody decided they didn't want to go to law school anymore. Now this shows you, right, that things. Well, first you can't label every single point on this. This is like at the limit of this 50 or 60 or 30 or 40 data points here, and that's already kind of too much. You could show it like this. With the zero baseline, I don't think that contributes a whole lot extra, other than to know that 40,000 is a larger number than 0. In practice, we're often working with data that sort of look like this, for example, where we want to organize a lot of information. And so we're doing a lot of labeling here. Each panel is labeled, but each data point is not. And we do a lot of design work here to organize the data in a way that we go from high to low average, and we in these kinds of faceted or small multiple plots label as much as you need, but we don't label every panel, but instead we try to leverage sort of having the same labels carry up or across in each case, which is sort of the trade-off that we're looking for, is that we're trying to give people enough signposting when they look at it to understand what's happening, would present a pretty information-rich graph that wouldn't. It would be hard to tell these trends if you presented the data in tabular form, and it would be very, very difficult to understand what was happening if you were trying to show the numbers. Yeah.
Related to that question, it seems to me that a lot of the visualization work that's been done is presuming a static graph like this. It's on a page or a static graph on a slide. Whereas we do have the opportunity for a lot more interactivity today. Do you have any thoughts as to the goods and bads, when and when not?
Yeah, so I think that, let me see if I've got a few practice slides. I think that I do have some thoughts, like that, and you're right that like most of the stuff that I've done myself has been producing sort of a static, image, essentially, to go in a journal article or in a book or something, as opposed to an interactive web page. And we have we have better tools now for producing interactive visualizations. And I would say that I'd say there's like a space of kind of uncontroversially really great interactive applications. So in particular, kind of highlighting particular data points, or being able to pick out a country in a trend, for example, or here's what this to identify on some third variable, like here's who this is, or here's what this point is specifically. And so there's, with D3 or with Shiny and R or the Python tools, you can do that. And then the question is whether or not the tools that we have to animate data over time, whether they contribute more or less than sort of static representations have. Let me see if I have an example of the former. I think I've got. I think I have an example of an animation that is kind of at the borderline of usefulness. There we go.
Related to that, do you know of particular people like Tufty that is talking about this in a sensible way that you can use as reference?
Well, I think that a lot of, I think that, I don't know that there's like a definitive piece of work that quite yet, in part because the tools are developing. I know that sort of people like Mike Bostock and others who develop D3 are very good at, in general on the question of how to represent motion in graphics. Here I'm just dumping this into my. So here's the thing I made just as an experiment the other week. So there's a.
We're not seeing.
I know it's not. It's coming up. Sorry, just a second. I just want to. I just want to make sure it doesn't start playing too soon. So the baby name database, right, is something. Or, U.S. Social Security Administration for baby names. The woman who developed that baby name Voyager website, one of the things she noticed in the data, she noticed this very interesting feature of this is not the right one. This is the girls. Boys is much better in terms of variation. She noticed this interesting fact about the distribution of names. We know that names, come and go in terms of their faddishness, and the data, the baby name data, allows us to see that very straightforwardly. But one of the things that's true in the baby name data that isn't so obvious, there we go, is the distribution of letters of the last letters of boys' names over time in the United States, right? So here we have our distribution. Now we could represent this in all kinds of ways, right? We could have like a small multiple that has 26 squares. That's too much. We could plot just the time series over time for each letter in terms of prevalence, which actually works very well, particularly if you want to just highlight a particular letter. Or we can animate it in this way, where we can just sort of set it running. This kind of like horse race animation has become popular recently. What you see is that in the middle of the century, after the Second World War, after a period of relative stability, something starts to happen and keeps on happening. Yeah. And so the last letter N. Now you can think about like the children within this age range. This is looping now that who are boys and have this is your sort of Braden, Jaden, Jackson, Kevin, Colin, Aiden. There's so many. And it's not an illusion, right? The last syllables of the last name N really take over. So for certain sets of effects, that's a very effective way of sort of looking dynamically at the data. That doesn't really fully take advantage of what you could do with animations or movies, but each additional feature that you load, and particularly with motion, you're asking the viewer to do more. And that's where the tricky part is. Like cognitively, again, like is it effective in trying to get across what it is that you want people to see? Interaction is nice because in principle it allows the viewer to drive their exploration of the data set themselves. But anytime you introduce an additional dimension or mapping or channel that you're transmitting information through, then you're asking readers to do more or viewers to do more, and it's hard to beat the sort of workhorses of data visualization like histograms and scatter plots. Just once people understand them, those remain extremely effective. Yeah.
Might be a bit of a left field question, but what about data representation for the visually impaired? And do the same sort of cognitive features sort of stand out and are helpful in that space?
So one of the things that and this is one of the reasons why visualization can't be just the answer to everything, right? There's a lot of heterogeneity in the viewer population, and so you have to attend to that as a designer. One way that I think the tools that we have do pretty well is in terms of variability in seeing color. And so the sort of color palettes that we use by default that are things like Viridis are stable with respect to varying kinds of color blindness, and so we can manage that. There's a very interesting article, and I'm going to forget the guy's name now, about sort of representing data for the visually impaired. There's a in its very early stages, there's a movement to explore the world of data sonification, and with some very interesting.
The yield curve.
Yeah, right. Yeah, there's different people looking at usually time series, because cross-sectionally it makes sort of less sense. But looking at sort of time series and trying to map into sound features of data in interesting ways. And again, it's the kind of space where someone like me I'm not qualified to sort of assess how successful it is. But you really get a sense of how much conventional dimensions there are, or how much taken for grantedness there is in visual representations of data when you try to interpret auditory ones, if that's not what you're used to doing. So we're pretty good on color, we're pretty good on making sure that people, represent data in a cleanly designed, uncluttered, easy to see way. And then there's this interesting sort of penumbra of work on different modalities altogether for representing data.
We had a presentation on that a year ago, 2 years ago.
Oh, yeah.
We were at SAS, this group at SAS, and they have an engineer at SAS who is blind, who's doing a lot of the development work.
Yeah, there's like a little package for R now, I think.
It's basically a screen reader for graphs that turns them into music.
Wow, yeah, there's an old Douglas Adams novel that explores that, and it's really interesting to see like it appear as actual software. Yeah.
Just found there was a post on flowing data a couple of weeks ago. A guy who moved from Bloomberg Business Week to Bloomberg, and made some really insightful comments on understanding the nature of your audience. When he was creating visualizations for journalism, he had to assume a general audience that wasn't familiar with visualization, that wasn't familiar with the topic, but making something that's going to be on a screen in a Wall Street trading desk, it doesn't matter what the learning curve is. They'll get up that.
Yeah.
What's important is that they can see what they need at a glance. And
yes.
And they have entirely different expectation. At the zero baseline, nobody cares.
Yes, exactly.
The learning curve doesn't care. What they want is it helps them do their job and make money.
Right, and if you're used to looking at data, I mean that's the reason. That's a very general point. Like that's the reason that graphs in scientific journals, will have a different set of standards and a different set of demands that they place on the designer. And so for example, if you're publishing a paper in a specialist journal, in many of the hard sciences, the chances are that the journal is going to want like 1 or 2 graphs at most that just tell the story of the paper. And it's like, here it is, and those will be very dense and require a lot of training in order to interpret. And that's a very different task. It does not, many of the same sort of principles apply, but it's a very different task from presenting something similar to a general audience. I think that the tools in R, for example, the way that R works, the way ggplot works, encourages us to think about building up visualizations in a layered way, and in a way that can be beneficial to how we interpret the data. Right? You can tell a story in a way that's reflected in the code that you write, a step at a time. And so here's a graphic of flipped counties in the 2016 general election, ones that flip one way or the other, either pro-Trump or pro-Clinton, with picking out counties that have a relatively high African-American population and sort of labeling the state that they're in. So there's like a bunch of different layers in this data, but we're only interested in the counties that flipped as opposed to all of the counties. You can just about make out this is a nice case of even more gray on the base layer. But we can build if you're presenting a story to a general audience, then one of the things that you can do is for example, take a plot like that and start with the base layer, and here's everything, right? And then gradually build it up. The code doesn't matter. We'll add this layer on top, picking out the counties that we're interested in. We'll add third layer with some guiding information, and then we'll add finally a bit of polishing to pick out to enable the counties, right, that were by state, right? And so there's like 4 or 5 layers in that graph. You can present it as a finished object if the audience is right, or also when you're working an argument through an audience or you're showing it to people, you can sort of take them with you through almost through the process of construction of the graphic in order to say, well, here's the basic data, here's the segment that I'm interested in, here's what I want to show you about it, and sort of just use each stage of your slide as a way to add an extra layer of information. And things like tools like ggplot make it very, very easy to produce graphs like on that layered basis. And so there's this nice affinity between the narrative dimension of making an argument and explaining something to an audience and the coding involved in actually presenting or producing a graph a piece at a time.
Hi. Could you repeat again what you were showing as far as the hurricane slide? Because it seems to me like the most accurate one in using the grayscale would have been the more difficult one.
As opposed to, so this is the slide, this one?
No, when you were showing the map and everything.
The hurricanes.
Oh, the hurricane, right, yeah. Yes, so I'm sorry, I misheard. Yeah, let me go back to the, yeah, and so you're right. Let me just find it. So your idea is that this, for example, the grayscale is easier to...
No. For me, it's easier to, like the first one.
So here's the...
Yeah, that one.
Okay. And so this would, like the... So is it easier for you to understand what's happening here because you're used to looking at the rainbow scale, or you find that more intuitive? I mean, that's a reasonable, there's heterogeneity in audience reception, so it's interesting to...
Well, when I'm seeing those maps, I'm interested in getting determining how many inches of rain and how strong the winds are going to be. So, especially since you mainly see it on either your computer screen or the TV, it's easier to make the contrast between the areas.
Yeah, and so it is the advantage of the fact that the rainbow palette is very sort of high saturation does mean that there are these clean distinctions between the areas. The challenge of, at least experimentally, with what we know from sort of testing people on this is that imagine if you didn't have this scale, and if we just showed you the scale in colors, and we asked you to arrange them in order from high to low, right? And how would you? If we just showed you this bar here with none of the numbers attached, we said, okay, here are these segments. We'll give them to you as like little pieces. Put them together from the lowest value to the highest value along the spectrum. What you find is that some people would flip the greens in different ways. Some people would flip the reds in different ways, right? They'd put this one to the right of this one, for instance, depending on their own judgments. If we show them this scale, they don't make that sort of. They might have a much more consistent set of choices about which ones represent the low values and which ones represent the high values. There's still variation sometimes, but they're much more likely to arrange them in the order that we actually need to present them on the scale than in this case.
But that's not what the green to red does. That wasn't the intention of coming up with that scale. Scale is going from a red center, high saturation, through a medium saturation in the middle, or a 0 point, going to a green or lower probability of high winds. So this is a U-shaped saturation curve intentionally so that people can visualize bands of safety or probability of low winds out of the rest of the map that's uncolored has to be considered.
Although this isn't a diverging scale, right? There's not a midpoint that the two sides are diverging from.
I understand that, but what I'm saying is the green saturation is you're getting to you're getting to green,
Yeah,
which
but-
is good.
Right.
It's like when
Yeah.
I get to high saturated green, then I'm going to the good place to
Right,
run
that it's
to.
safer.
Yes.
Right. Yeah, that's the intention. I see what you mean. No, that's right. And so that you've got high danger,
And
moderate
so,
danger,
I was
and a high
raising my
probability of
hand
low
while you
danger.
were discussing
Yeah.
this, and
Yeah.
as you gradiate as you correlate the percentage saturation, you remove that knowledge from the graph. And so that's why it was confusing to me. What you were saying is that it seemed like you had
I'm
There are
sorry,
two-
the statistician's going to have a panic attack. That's not what that means. That scale means probability of being in danger. Red is high,
Yeah.
green is low, and for some reason tan is 0. And that's the problem with that scale. You actually laid a meaning on the numbers based on the colors that doesn't exist.
well,
The scale is from 0 to 100.
you're critiquing my interpretation.
Well, yeah,
You
because
can say I'm completely wrong. That's fine. We disagree.
you changed
Well,
the meaning
no, but
from 0 to 100.
there is in fact a scale. So the designer of the graph wants to convey a relative degree of risk from 0% to 100% risk for the thing that's being measured, which is the probability of storm force winds.
And culturally, we do tend to associate red with danger more than we do.
Which is why people choose the
Except in China.
which is why people choose
We
the rainbow scale.
It's like red is good in China.
But it's not. I mean, you can have scales that have a midpoint in this way and diverge, but this is not like that's not meant to be what's being conveyed in this.
The safest region is outside of there, and so that if that's the case, that should all be green because that's really safe.
Or white.
But this scale, you can
Yeah.
The other one seems to take that way.
I'm not sure. I guess I've never really thought into what exactly was the design behind it. As a kid,
Sure.
like,
If
I
you can,
noticed
but
is
usually
I need to have a
when
clear
you're
distinction of
living
the
in a
areas to
storm
determine
area,
if I have to
when you're deciding how far to run, that's what you're trying to
Right.
do.
Yeah, that's quite reasonable. The thing is though, for example, in the grayscale version, maybe it's easier to see in the gray. Like that, here you can see. Well, the dark areas are where you should be evacuating.
I think that was
right, and the lighter areas there's
how
much
they
less
go.
risk. That's the and you can still clearly delineate the zones as represented in the scale. It chunked it into deciles. But it's clear that there's this reflects the fact that there's a decline in probability of this force wind as you move out into this area. Yeah.
So what I'm finding really interesting about this discussion, as well as the charts themselves, is if I look at the charts and I try to remove my cultural bias, there is no question this chart is way clearer. Here's the rain, there's no rain. But I have been trained from childhood to look at that rainbow scale, and that's what you had said earlier. From tinyhood, right? All I need from the local news is the weather report, and that's this.
Yeah.
So when you try to put that non-culturally specific visualization, I'm like, oh, forget it, I like it.
I think that's quite a reasonable point. We see this, for example, and there are cases where that sort of conventional interpretation is something that you just have to deal with as a designer. So, for example, in political maps, so Democratic blue and Republican red, like there's no point in as a designer trying to choose like a nicer orange or a green. Right? Those colors have cultural meaning in that context, and so you should defer to that. Other times, for certain kinds of categories that have cultural meaning, you don't want to defer to it, right? So you don't want to be producing graphs that are blue for boys and pink for girls, for instance, right? So in those cases, you would say, no, I'm going to find some other colors to that do the job just as well. In this case, I think that we can still distinguish between the red, danger, green, safety question, which is a reasonable feature of this, like a good feature of a graph like this, and the question separately of, well, which order of green, if you just glanced at it, like why is this like much brighter green, not the outermost layer? And some people will choose that, right, if they have to order it, whereas in the desaturated, still red to green image, there's no ambiguity about the ordering, or much less ambiguity about the ordering, even within this kind of cultural context of red to green.
Part of what's going on in that more saturated image, though, is we know that the inside of that card
You're
is
looking at a map, yeah.
and it gets safer as you go out. And we're adding that knowledge on top of the color scales.
Yeah.
And I just think the saturation
Yeah.
just makes that easier to see.
Yeah, and you know, I mean, there's also one of the ongoing issues with these kinds of risk cones is that you know, people think that this is the hurricane.
Right.
Right. and that's, I mean, that's like, and so they have to see, you have to say, oh, not all areas within the cone will have equal impact. You're trying to get this across that this is, and so fundamentally you are still kind of trying to represent the probability of something happening over this space, something bad to something good, or less bad. But then people will look at this and be like, well, this is Hurricane Dorian, this whole thing, you know, as opposed to, you know, and that's, I mean, again, as an information designer, especially in a context where you're trying to communicate something of importance to an audience, you have to sort of understand it's a two-sided process. So there's, you know, the concessions that you have to make if you're into the National Weather Service are ones where you're, well, they're not helped by, you know, somebody drawing with a Sharpie on the outside to encompass a larger of what he took to be the hurricane. Right?
All right, I think we're going to call it at that. Let's give